This is Dr. Holt. I want to work two problems here having to do with projectile motion. This first problem is the famous monkey problem. Here we want to find out what is the minimum initial speed of a dart to hit a monkey before the monkey hits the ground. If the monkey is 6.2 meters above the ground and the dart is launched 60 meters away horizontally and the dart is launched 5 meters above the ground. With a problem like this, the first thing you want to do with this problem is try to find out how long it's going to take the monkey to hit the ground. Now the monkey is going to accelerate downward at a rate of negative 9.8 meters per second squared. Its initial velocity is going to be 0 when it first drops. It's going to reach maximum velocity when it hits the ground. We go back to the equation that delta y is going to equal to vi in the y times t minus 1/2 times 9.8 times t squared. Since the initial velocity is 0, we can ignore this part here and let that go to 0. At this point, we can put our displacement in. We're going to fall 6.2. So our displacement is going to be negative 6.2 meters. So that equal to, and then we go ahead and do this. That's negative 4.9 meters per second squared times t squared. Divide by 4.9. So negative 6.2 divided by negative 4.9. We take the square root of that. That will give us our time value. And when we do that, we will get a value of 1.12 seconds. Okay, so that's the time it's going to take the monkey to hit the ground. From this, we can find out what our horizontal velocity would have to be of the dart gun as it shoots horizontally. Again, this is only the horizontal component. So once we have no acceleration as I move horizontally, the only acceleration we have is gravity coming down. We do not have to include acceleration in our horizontal direction. So we can just go back and say that delta x is going to equal to vi times x times our t. We know our displacement is going to be 60 meters. We're going to solve for our velocity in the x direction, and we're set our time as 1.12 seconds. When we do that, we can get vi in the x direction a value of 53.57 meters per second. Okay, again, that's going to be our velocity, horizontal component of our initial velocity. Alright, now what's going to happen is this monkey is going to fall all the way down to here. So we'll just draw a circle here. The monkey's going to be right at this point. We want to find out how much vertical velocity is going to be required to get the bullet to hit right at that point. So we can go back to our kinematic equations. Again, I'll write them all down. We know that delta y is equal to viy times t minus 1/2 times 9.8 times t squared. We know that vfy is equal to viy minus 9.8 times t. And we know that vfy squared is equal to viy squared minus 2 times 9.8 times delta y. Alright, so we can go right to this equation right here, and we can solve for our velocity here because I know time, I know displacement, so that's the only unknown here. We'll use that equation. Now my displacement for the bullet, at this point I'm going to fall 5 meters. So I'm going to fall negative 5 meters. So we use this equation and put in negative 5 meters is equal to our initial velocity in the y times our time, which is 1.12 seconds, minus 1/2 times 9.8 times 1.12 seconds squared. We'll move everything to the left side. That gives me minus 5. Go ahead and simplify this. This is plus 4.9. It's going to be plus, I'm moving the other side, times 1.12 squared. All I have to do now is divide by 1.12. When I do that, I will get my initial velocity in the y direction, a value of 1.024. meters per second. So if we draw this in component form or vector form, we'd have a we'd have a velocity coming up and have a velocity going over. This value here would be 1.024 meters per second. This value here, we found it earlier, was 53.57. All we have to do now is find out this value right here. We can just go to Pythagorean theorem and say that VI, which is this value right here, is going to equal to the square root of 1.024 squared plus 53.57 squared. When we do that, we're actually going to get a value that's very close to 53.57. It's going to be slightly more than this. It's only because this value happens to be so small. And that would give me my initial velocity. Now, if I need to find this angle here, theta, then we could say that theta is just going to equal to the inverse tangent of 1.024 divided by 53.57. Again, that would just give me my angle theta if I need to do that. And I'm going to find my calculator real quickly. I can try to run that. All right, see what we get here. We take 1.024 divided by 53.57, second tan, second answer. That gives me a very, very small angle of 1.095 degrees. All right, so that's how you do that problem here. Again, take note, it doesn't matter what this velocity is going to be when it comes out of this dart gun. As long as the trigger is pulled at the exact moment that monkey lets go, you're going to hit this monkey. If this, no matter what this distance was here, this could be a squirt gun, it could be a high-powered rifle, it could be anything, but you're going to hit that monkey if you aim right at it, as long as when you pull the trigger, the monkey falls at that exact moment. All right, let's look at another problem. This one here, you have a projectile. It's launched from the ground level with an initial speed of 57.2 meters per second. We want to find the launch angle such that the maximum height of the projectile is equal to the horizontal range. And what I'm trying to say here, this being the horizontal range between basically here and here, I should actually do center mass, something like that. Let's just do center mass about here and here. This distance here, we'll call this delta x, must be the same distance as this value right here. So that's what the problem's really trying to say. The distance here and here will be the same as this distance here and here. All right. Now we do know that we can say that delta x is going to equal to the velocity, which is 57.2, times the cosine of the angle theta, well, this being theta, times t. Now we can say that. All right. So that means that this value here must also be 57.2 times the cosine of theta times t. All right. A couple things we do note: when we reach the maximum at the top, then the vertical velocity here will equal to 0. Vy here will equal to 0. The horizontal will not be 0. It's still going to be traveling 57.2 times the cosine of theta all the way through this parabolic, this parabola as it goes back down. All right, so let's go ahead and see what we can do here. Let's see if we can find out. What time is here. Now we do know a couple things regarding time. We know that Vi in the y direction here is going to equal to my velocity of the bullet, which is going to be 57.2 times the sine of theta. We also know that Vf in the y is going to be negative 57.2 times the sine of theta. Because if it goes up 57.2 times the sine of theta, it's going to come down 57.2 times the sine of theta. So let's go back to our kinematic equation that says that VF in the y is equal to VI in the y minus 9.8 times t. We'll put minus 57.2 times the sine of theta here for VFY is equal to 57.2 times the sine of theta here minus 9.8 times t. I'm going to move this over to the other side. When I do that, and then look what happens here. That's going to give me 2 times minus 57.2 times the sine of theta divided by negative 9.8 is equal to t. Now notice here your negatives here will cancel out here and here. So our final answer would be t is equal to 2 times 57.2 times the sine of theta over 9.8. Okay, we'll go ahead and just simplify that a little bit more. So we'll take 2 times 57.2. And I think I'll leave the 9.8 in the denominator just so I don't get a rounding error. So I'll say time is equal to 114.4 times the sine of theta over 9.8. All right, so we got time in terms of theta. All right, so now let's go back to talk about what's going to happen when we reach the top. Again, we know the initial velocity, or sorry, final velocity here is going to be 0. So we go back to the kinematic equation that says that VF y squared is equal to VI y squared minus 2 times 9.8 times my delta y. Again, we know at the top we're going to get 0. We know this value here is just going to be 57.2 times the sine of theta. That's my initial velocity. We're going to square that minus 2 times 9.8 times delta y. And again, we know delta y is this value right here. Oops, moved on me, hold on. Oh, skipped one, I'm sorry. There we go, sorry about that. That's going to be 57.2. Okay, one more time, sorry about that. Cosine of theta times t. However, we already just figured out what t is, so I'll take t out here. We'll put in 114.4 times the sine of theta over 9.8 here, okay? Okay, now what I'm going to recommend here is go ahead and square both of these. So we'll make this 0 is equal to 57.2 squared times sine of theta squared minus 2 times 9.8 times 57.2 times the cosine of theta times 114.4 times the sine of theta over 9.8. All right, now we want to go through and see if there are the things that we can simplify. Well, the 9.8 is gone here and here. Why don't I divide everything by the sine of theta, because 0 divided by the sine of theta is still 0. So I can get rid of this one here. I can get rid of this one here. Now, one of the things I could do, remember earlier we said that 114.4 is nothing more than 2 times 57.2 right here. So if I divide everything by 57.2 squared, I got, so 0 divided by 57.2 is still 0 here. Now, if I divide both sides by 57.2, this is gone here, this one is gone, and then this one is going to be gone because this is nothing more than 57.2 times 2, and 57.2 times 57.2 is 57.2 squared. Again, you don't have to do this. I'm just trying to simplify this problem as much as I possibly can. Now, let's look and see what I end up with. What I end up with is going to be sine theta minus 4 cosine theta here. All right, so now we're going to have something that we can probably try to simplify. I'm going to move the sine theta to the other side. That gives me minus sine theta is equal to minus 4 cosine of theta. I'm going to divide both sides by negative cosine theta. That's going to give me the tangent of theta is equal to 4. So theta is going to equal to the inverse tangent of 4. And when we do that, we will get an angle of 76 degrees. So let's see what we're doing. The question was find the launch angle. Well, we just found the launch angle, and the launch angle would be 76 degrees. All right, and that's what's going to find this angle here is 76 degrees. And just go back to the problem, make sure, find the launch angle. All right, that's a really, really good problem. Again, just work through it very methodical. Use the kinematic equations where they're applicable, and again, you've got to substitute in for time here because you want to get down to the least the number of variables, and what I ended up getting was the only unknown I had was theta. From that I could solve the problem.